So this video is going to explore how the shape of a molecule that's dictated by its Lewis dot structure, how its shape alters or determines something, a quality of a molecule called polarity. And we're going to see that this quality called polarity is also tied to this term called electronegativity. So we're going to explore and define these two topics with regards to shape in this video. So in the structures that we have written so far, when we have been designating or showing shared electrons between two atoms in the form of a bond, we've been writing that in the form of a dashed line for a single bond. And that dashed line sort of is assuming that those electrons are shared equally. So for example, looking at this OH bond, the electrons between the oxygen and the hydrogen are assumed to be shared equally between those two atoms. Well, in reality, that's not exactly correct. It turns out that in many covalent bonds, electrons in that bond are shared unevenly. In the case of this OH bond, it turns out that more of the electron density, which is illustrated with these little purple dots, more of the electron density is focused by the oxygen than by the hydrogen. And so we can show that in a cartoon way with these little dot picture. We can show it also in terms of doing this little negative sign and positive sign here, just to show that in this covalent bond, there's a bit more electron density toward the oxygen than the hydrogen. So this concept of having a bond where the electrons are not shared equally, that concept is called polarity. And polarity comes about because of an element to attract electrons within a covalent bond. And that term is called electronegativity. So we would say, looking at this picture on the right-hand side, we would say that oxygen is more electronegative than hydrogen because more of the electron density is by the oxygen. Okay? So all elements have some value or associated electronegativity with them. Knowing what those values or trends are can help scientists say something about how polar a bond is. And when we say polar in terms of chemistry, we don't mean polar bear. We mean separation of charge, meaning a distinct difference in electronegativities between two atoms in a covalent bond. So we would say in this OH bond that it is polar because there's a separation of charge, and that polarity is due to the differences in electronegativity between the oxygen and hydrogen. So if you go on in chemistry and you learn more about periodic trends, you'll learn that electronegativity, when looking at the periodic table, electronegativity for elements increases going up from left to right and bottom to top. So fluorine is the most electronegative element that's out there, with cesium being the least. So you can use that trend to say something qualitatively about the electronegativity of an element, but there's also a scale, an electronegativity scale that it is associated with each element. The higher the number of that electronegativity, the more electronegative that element is, or the more that element wants to hog electrons in a covalent bond. So those electronegativity values can be shown or tabulated in a table like this that you will be able to use for exams and quizzes. And the reason why you'll need to use this table is because you're going to need to use it along with this definition of electronegativity, polar and nonpolar, as to say something about the quality of a covalent bond. So If you go on in chemistry, you'll learn more nuances, but for this class, we are going to consider covalent bonds to be either nonpolar or polar. In a polar bond, there is a big separation of charge between the two atoms in a bond, meaning that there's a big difference in electronegativity. Nonpolar bonds have smaller differences in electronegativity. In a more quantitative sense, we could say that if you have a bond and you take the difference, that's what this delta means, if you take the difference in electronegativities between those two elements that are listed here on this table that you will be given, if that difference is 0.4 or less, then that bond is nonpolar. If it's 0.5 or greater, then we can say the bond is polar. Now we're going to do 3 examples on the next slide to determine if a bond is polar or nonpolar. But when you do this calculation, this difference in electronegativity, difference means subtraction, but you always want to subtract the larger number in this chart from the smaller number. And the electronegativity values, you can see they're on the bottom here. So like lithium would be 1.0, boron would be 2.0. You always want to subtract the bigger number from the smaller number. So you want your delta En always to be positive. Okay? So knowing this qualification and this table, let's say something about these 3 bonds that I have down here. Let's determine if each bond, HH, CH, or NH, is polar or nonpolar. Now, if it's polar, we're going to do something that's called drawing the dipole. You'll be doing this in your Lewis dot structure lab for next week. But with polar bonds, many times scientists will show that separation of charge or that polarity by drawing a dipole, which essentially is drawing an arrow by the bond from the smallest number. And when I say smallest number, I mean the smallest electronegativity number, so the smallest En number, to the element that has the larger En number. Okay? And that arrow, that's in blue here, that is called a dipole. Sometimes scientists will also put a little plus sign on this side just to show that that is the positively charged end and the negatively charged end. You don't need to do that unless you want to. The main thing we'll be looking for is if I ask you to show a dipole for a polar bond, that means draw an arrow from the atom that has the smallest electronegativity value to the largest electronegativity value. Okay, so let's try these 3 examples. HH, I want to know if this bond is polar or nonpolar. To figure that out, I need to take my delta En, my difference in electronegativity between the 2 atoms. They're both hydrogen. They both have an electronegativity value according to the chart of 2.1. Making that difference gives me a 0, which is 0.4 or less, so it is definitely a nonpolar bond. I'm going to do the same kind of calculation with CH, although this time using the electronegativity of carbon, which is 2.5. Doing that difference gives me 0.4, so that is a nonpolar bond. Now let's go to NH. We're sort of traveling down or traveling across the periodic table. Nitrogen has an electronegativity value according to the table of 3.0. When you subtract the hydrogen electronegativity of 2.1, that gives you 0.9, which according to our rule of thumb here, that would make this NH bond polar, and therefore our dipole, our arrow, is going to be pointed towards the nitrogen, from the least electronegative atom to the most. Okay. So that's how you determine if a bond is polar or not. In the next and final video for this chapter, we're going to talk about how we can use this concept of electronegativity with shape to say something about the polarity of an overall molecule.